Let's start. Uh, I'd like to thank the organizers for having given me this opportunity to speak at the Struchkov meeting. And okay, look, in this brief talk, I'd like to tell you a little bit about crystal engineering. And since I'm speaking for a crowd that is largely from Russia, and this is in a tribute and a memory to Professor Struchkov, whom I had the pleasure of meeting many times in the 1990s, uh, and many of his colleagues. And I'm pleased over here because he was important for me. I was a young man when I used to talk to him, and coming from the country of Kitaigarodsky, he gave me a different philosophical approach to the whole subject of crystal engineering, because you see, I come from the other direction where we started looking at interactions more than close packing. And when you think about these two fundamentally philosophically different ways of looking at the subject, you realize that there is no contradiction in the end. And finally, everybody reaches the same point, whether you talk about a crystal as close packed where the interactions perturb it, or whether you talk about the interactions and then you say that the close packing comes and perturbs it. Finally, you end up in the same spot. So I would say that in terms of my growth in the subject, I owe, because I never met Professor Kitaigarodsky myself. I was too young. So he was able to tell me. Also, people like Professor Zorki, I remember, and then Struchkov's associate, Professor Shishkin. Many years later, I have had long discussions with him till his sad death a few years ago. And so I would say that speaking before a Russian audience brings back many, many old memories. Now let's go further. What is crystal engineering? It's the design of molecular solids, the internal structures, external morphologies. All this is well known. This is my 2011 textbook, which has now been, uh, you know, used widely by students everywhere after the 1989 book. A discipline of various diverse areas. And so what is the core issue? The core issue is you cannot predict structures with a modular approach with functional groups. Because functional groups, as used in organic chemistry, they are functional. I mean, they pertain only to that particular group, nitro or hydroxy or whatever. And so the behavior of the molecule depends on the nature and positioning of all the other groups in the molecule. So crystal structures are not related to molecular structures in simple ways. If you take the close packing extreme, then you will have to say that you have to take the whole crystal as a whole, and many of the modern methods of structure prediction go on this line. Now, look at this example. This is a very nice example because this is a carboxylic acid, but it's a very strange one. It's a cubane acid, and you can see the conformation of the carboxyl group is both syn and anti in the same structure. There are very, very few structures, mostly all cubanes, which come in this series. And then you realize that instead of forming the usual carboxy dimer, which is preferred with these acids, uh, this one has, actually I call it a crazy pattern. And this is because of this all important CHO weak hydrogen bond between the activated cubyl hydrogen and the oxygen here. So it is actually the tail that is wagging the dog. This CHO is changing the entire OHO hydrogen bond pattern. So this sort of tells you the dilemma and problems that we had in crystal engineering in the 90s, at the time when I was talking extensively to Professor Struchkov about matters like this. So some simplification is needed. The simplification, of course, comes through the, at least in my eyes, through the supramolecular synthon approach, which I proposed in 1995. So I think synthons are too well known by this audience for me to start talking anything more about it. And anyway, all this is the introduction to the what I really want to tell you, and that is where the subject of crystal engineering is going, not where it came from, because where it came from everybody knows. So these are these synthons, and then they are a kind of a modular unit, which is a better representation for the structure than the functional group. That is important. Functional group, solution organic chemistry, synthon, crystal engineering. Now, these are all these intermolecular interactions. So many of them: hydrogen bond, CH5, van der Waals, halogen bond. A lot of good work on halogen bond is going on in Russia. I can talk about the work of Vadim Kukushkin and so many others. Actually, there's a lot of stuff going on halogen bonds today. When we wrote this review article in 2014, it was still, we had to educate the people. And so what about these halogen bonds? They are like hydrogen bonds and yet different. And I think this is a very fascinating story that is only now coming out. The last word on halogen bond is not known. After halogen, we have also pnictogen hydrogen bond with the group 5 elements, then group 4 tetral, and so on and so on. So this is a continuing panorama of these bonds where hydrogen bond started the whole story. Now, this is a very recent example of how the synthon theory can be used. You can bring in as many as uh, 4 different organic molecules, all of them solids at room temperature, in a stoichiometric ratio in a single crystal. And this is unprecedented. People have, of course, worked with binary co-crystals for, well, almost 200 years, since Wohler discovered quinhydrone in 1841. And then, of course, the ternaries started 10 years ago or 15 years ago, maybe 20. And now we get into quaternary. Please remember, these are not solid solutions of the Kitagorodski type and so on. There are 4 organic compounds, each of them solid at room temperature, and all of them go into a stoichiometric single crystal. This is actually quite difficult to do. We have about 30-40 quaternaries, and mostly they are from our group. Nobody else has been able to do this. Now, I'm just giving you an example. Now, how does this strategy work? Strategy works in the sense of, you have a molecule like this red thing TMP, which is, for example, in 2 different crystallographic environments in the crystal, shown by this wavy rectangle and this straight rectangle. I'm talking about the picture on the extreme left hand side, in case you can't see the mouse that I'm moving. If you can see the mouse that I'm moving, very good. Now, this is the 2 TMPs, and therefore they are crystallographically distinct. So one of them can be replaced. They are not the same chemically. So this is what we have done. So instead of having MRES wavy TMP, we've got MRES. This TMP stays the same and in fact picks up another one, PAH. And now you see what has happened here is we have 2 MRESs in different crystallographic locations. So once again, one of them can be replaced now with DPE. And so this is the overall quaternary co-crystal stoichiometric, which we published in 2016. 1, 2, 3, 4. 4 different molecules in the same crystal. Now, let's go further. Now we go to the future. Now the future, I have now about exactly 32 minutes. So about 3 minutes on each of these. Pharmaceuticals, solid state reactions, thermosalient materials, framework solids, MOFs and COFs, property engineering, solar energy harvesting, water splitting, polymer science. So we wrote a viewpoint in Angevente a couple of years ago. And this is the journey of pharmaceutical co-crystals, which is one of the hottest topics in crystal engineering today. So starting off with the synthon, which I proposed in 95, we had Mike Zavorotko, who talked about pharmaceutical co-crystals in 2004. Then these things entered the area of formulation. And then we had the first commercial things coming out, and now finally scoring a home run, we are actually having marketable products. So it's been, quite a rapid journey, just 20 years to go from an idea to a marketable product. This is quite amazing. And then it tells you why this crystal engineering field is so hot today. Now, this is very important. This is the US FDA. In 2011, they gave a kind of retrograde set of guidelines for the definition of co-crystals. After a lot of pressure from the community, they have now redefined pharmaceutical co-crystals, and they say that it opens up opportunities for engineering solid state forms. Notice this word engineering solid state forms, beyond conventional solid state forms of an active pharmaceutical ingredient, such as salts and polymorphs. So salts and polymorphs is something everybody knows about. Now they've said co-crystals also comes into this. So immediately once FDA gives a blessing for something, then there will be a lot of research and there will be definitely lots of new products. Now, why are these pharmaceutical co-crystals so important? This is the bottleneck. You see, you want class 1 drugs with high solubility and high permeability. But today, the way in which the drugs are designed, many of them come in the class 2. That is, the solubility is low, the permeability is high. Then, of course, you have this rotten category, class 4, low solubility and low permeability. Not so many in class 3. So the idea is we want to take these class 2 and class 4 into class 1, because otherwise it's, you may have a nice drug, but if it's not getting to where it's needed, then it's pretty much useless. So let's see what we did. We took these two, norfloxacin and sulfathiazole. You see, this is an antibacterial and this is an antimicrobial, and usually they are given together in many medications. Now, the problem with norfloxacin is it is very insoluble. Sorry, with norfloxacin it is very insoluble. Sulfathiazole is the one that is soluble. So now what happens is when you take a physical mixture of these things, you see this is the relative solubility. This is uh, norfloxacin. eh, This is sulfathiazole, and then now you have here the co-crystal. You see this red one is the co-crystal. Now, similarly, in the matter of permeability, it is best illustrated by saying this. So, you see, what is happening here is in the crystalline, let us take a physical mixture of norfloxacin and sulfathiazole. What really is happening here is that the norfloxacin behaves separate, the sulfathiazole behaves separate. So this is the permeability issue. There is a membrane here, only the sulfathiazole goes through, the norfloxacin gets stuck on the other side. So you have to really, the dosage in norfloxacin has to be very high. Now, the main idea of the supramolecular synthon, the importance of this norfloxacin sulfathiazole result of ours is that there seems to be now for the first time evidence for an extended supramolecular synthon in solution. So there is some interaction which is strong enough so that at the membrane, the sulfathiazole is able to drag the norfloxacin through, and it doesn't behave. The two don't behave like separate entities. They behave as one whole thing. This is the basic concept of synthon. This is the basic concept of supramolecular chemistry itself. And now it can be used in the real practical field of drug design and drug development. Let's go further. These are all the things that are now there. Let us take Entresto is the most famous one. The valsartan and sacubitril, which is now on sale in America as a co-crystal. These two things were given separately and now they are given together. So this is really big, and I think there have been some recent developments also in the last 1 month or so. We're going to see many more co-crystals being marketed. Now let's go quickly to solid state reactions. This is of course Gerhard Schmidt, and there was a meeting I attended, one of the last meetings before this COVID pandemic in the Weizmann Institute in Israel, where he's the person who really started crystal engineering off long ago, and this was his 100th birth anniversary. So that makes him, I suppose, a few years older than Professor Struchkov. Now, here were some of the things in the meeting. These are two of his most famous students, Meir Lahav and Leslie Lazarowitz. And here is me with Pierangelo Mitrangelo, a leader of the halogen bonding group. And we're all having a good time, not even imagining that COVID was going to hit us in a few months. So this is mechanochemistry. Again, a very big thing, very big in Russia as well. You people have been working on this for almost 100 years in your country, starting with the Second World War time. And mechanochemistry is now one of the, again, hottest areas of crystal engineering, because when you start grinding things together, they react in certain ways that they don't do in solution. And the literature on mechanochemistry itself is enormous, and it has got enormous industrial application. I will refer, of course, to the father of mechanochemistry, that is Professor Boldyrev in Siberia, who has recently written. I think he also is of a very ripe old age of 90 plus and still doing enormous amount of work. And then he talks about what's in a name. Yes, what is in a name? The thing is that the solid state reactions that have been proceeding. I mentioned Professor Rastogi from this country, Professor Toda from Japan. These people were all pioneers. They were well ahead of their times. Okay. And they were talking about things that nobody else could understand in their time. Now, very much later, people have realized the greatness of some of these wonderful scientists of the past. So, solid state reactions, they used, they're shrouded in the patent literature, industrial organic solid state reactions. This is where crystal engineering is going. Can you engineer a mechanical transformation to get novel products which are commercially valuable and required? So this is what it is. The whole thing is the competitor is the solution reaction. And in many cases, you see, you don't have to use solvents, and therefore you get, you don't have, get into pollution and all that kind of thing. So it's really, again, a thing of the future, and it is something where we go from the deep past and then come back into now into the through the present into the future. This is all going to be extremely important. Now, continuing on the same theme, we talk about the other end of crystals, that is mechanical properties of small tiny crystals. Crystals that are brittle, crystals that are elastic. In other words, when you deform them and then release the stress, then it comes back to the original shape. And crystals that are plastic, that is when you can deform them, but when you release the stress, it does not come back to the old shape. So these sorts of things, we call them therefore compliant and brittle. Within compliant, of course, you have plastic and elastic, and within plastic, you have bending, shearing, and so many things. So this is a new subject actually. It's a new part of crystal engineering. I would say that in our own way, we started this thing off in 2004, 2005, when we showed that crystals of hexachlorobenzene had this property of plasticity. Till then, people thought that all organic crystals are brittle. Okay, so now suddenly people started to think about this, and things moved along quite nicely. And we wrote again in accounts in 2018 with some of the people who are quite important. I would mention Panche Naumov, who is in the New York University in Dubai, then Calvin Sun in Minnesota, and Tomislav Frischik in McGill, Malla Reddy in ISER Calcutta, above all, who has done a lot of work on some of these things. Chris Bardeen in America, and I'm very happy to talk about Dr. Ghosh and Dr. Mishra. One was a postdoc, one was a PhD student with me, who have written a wonderful review in crystal growth and design. Now, please see, we wrote this thing in 2018, and after that, we have 1, 2, 3, 4, 5, 6, 7 reviews. These are not papers. So many people felt like writing reviews on this one topic. Clearly, this is exploding because it can be used in devices for sensors, you know, thermosalience, photosalience. The fact that the organic crystals are anisotropic in nature means that you can lead from them into all sorts of anisotropic properties. Let's go further. So here is the shearing. This is our very old example where actually Professor Mallareddy was my PhD student in those days. So he found that some of these crystals you can start shearing them, some of them you can start bending them, and we gave models for all the shearing, bending, etc. And the interested persons know about all these old papers. This is what sort of led to this whole area and its quantification. Now this is of course elastic deformation. Remember that in an elastic deformation, the restoring forces have to be strong enough. So you can take a spring and then you can distort it this way, you can distort it this way. And certain combinations of intermolecular interactions are needed to produce this kind of effect. And only a very delicate balance of interactions will cause an elastic deformation. Otherwise, deformations tend to go to the plastic stage. Remember one thing, that every plastic deformation starts with a small elastic domain. Every deformation is elastic at the very beginning. But many of these things, because of imbalance of interactions in the crystal, they go into the plastic domain very easily. So it requires a special set of circumstances to keep a crystal elastic. And this is the whole challenge here. And for example, okay, one more thing we found out in this exercise. This was a paper we published in JACS in 2017. By adjusting the interactions, we start here with 1,4-dibromobenzene, which is a one-dimensional plastic crystal. We can make it into a one-dimensional elastic crystal by simple substitutional changes. From that to a 2D elastic, because in this case the interaction has been calibrated. You can do the calibration in two directions, you get 2D elastic, and then an even finer calibration. Now I want you to see this last portion very carefully. The structures are the same and the properties are different. So the same structure gives you, with some combination of interactions, elastic, some with plastics. Now this is radically new, because chemists throughout, have been used to thinking that once you know a structure, you know the property. This example and other examples that have come like this tell you that structure need not be a unique limiter of property. Something can have the same structure and it can have different properties. This is something new which chemists are now getting used to. So, the three generations of crystal engineering, we have talked about that in the paper in JACS. So, we have a molecular structure, and from that you go to a sort of a crystal structure like this. This is what Kitagorsky was trying to do. Molecule to crystal. He wanted to do it in one step, and you really can't, because the crystal structure you get will be only approximate. You do need these interactions which are anisotropic in nature. So this is why Kitagorsky's model, in hindsight, I mean, this was a great model in its time. If you just take packing alone, it's not enough. You need these interactions. So the first stage was to look at the interactions. The second stage again is a retro step. And this is what I did with the 1995 supramolecular synthon thing. So the second step is not a forward step. You can't do it so easily in the forward direction. But if you start with the crystal, you can work your way backwards and find out what sorts of interactions will be needed. Now, we have proposed in these articles of ours recently, and others have taken this up, that in the third stage too, you cannot go so easily from crystal structure to property. You must start with a property and work your way back to a crystal structure in a retro way. More or less to say, I need this property, therefore, what crystal structure should I go behind? What many chemists do today is they say, I have got this crystal structure, let me see what property it gives. That is not the optimal way of doing it. Sometimes, it will work, but more often than not, this is a much more rigorous way of doing it. So the first step, first generation is forward, but the second and third generations are definitely retro steps. And this, reveals new ways of thinking. I've talked about property coming before structure. What did Mendeleev do finally in the periodic table? He said the property is more important. He said that, whatever he called gallium and germanium were not there in his time. And then he called them Eka aluminium, Eka silicon. That means he said something with that property has to be there. And this is why I am very much interested and keen to talk to a Russian audience, because I also know that these are, let me assure you, ladies and gentlemen, property coming before structure and not the other way around is a civilizational difference between structure coming before property. Structure coming before a property is a reductionist way of thinking. Property coming before structure is a holistic way of thinking. And I know there's a lot of discussion in your country now about whether you all are a civilizational state or a nation state. And I don't want to get into political controversies with you, but let me tell you, as someone who comes from a country which knows very clearly that we are civilizational, I think China and India today are the two countries that have no doubt about the fact that we are not nation states and we are civilizational states. it affects the way of thinking. So please remember, as scientists, the goals of science are the same, but the way in which we reach that goal can be very, very, very different. I always say, and I've always told my students, that Mendeleev scored in the matter of periodic table compared to Lothar Meyer, because Lothar Meyer was thinking in a reductionist way, Mendeleev was thinking in a holistic way. So today, with complex systems, unless you think holistically, I am afraid to say you will not make so much progress. So if people feel that Russia is civilizational and you've wasted your time after Peter the Great trying to go behind some Western model into which you don't fit, let me tell you, as someone who comes from a civilizational state, don't worry about it. Just feel free to, to feel whatever you feel like feeling. I mean, so let me put it like that. Now, finally, morphs. This morphs thing is a very big area. Okay, huge. And the thing is, this picture, a nice picture here. This is Prussian blue in a famous painting which hangs in Germany. And this is the first one of the morphs. They didn't know it was a morph, of course, but it is a coordination polymer. And this is that Prussian blue ferrocyanide or something. So today the framework, porous solids, easy to crystallize, 20,000 have been made. It will do catalysis, it will do separation, so many things. I don't have to tell you about all the things that MOFS does. Robson is a famous name, who was the first guy who showed a retrosynthetic way of making them. Yagi gave them the name MOF, and so today it's one of the hot areas. Now the problems. This is called elephant in the room. They are not lack of thermal stability. Zeolites rule the roost in petrochemical refining, naphtha cracking, bulk chemicals. Big ticket applications in energy are still missing. And there was a nice article in Chemistry World recently. For the last 15 years, the elephant in the room has been, where are the applications? Where are the applications in MOFs? Big ones. Can MOFs beat zeolites? Not yet. Can you find something else? We'll have to see. So the jury is out on this. And this is a more slide about detail. But even in the matter of capture of CO2, the current traditional methods of alkaline scrubbing are still cheaper than using MOFs. And also, with the price of crude oil going up and down, the methane fuel transportation and energy is still a distant dream. Tomorrow, 10 years from now, when natural gas becomes more important than crude oil, this may become even more of an adverse factor to do with MOFs. So really, I think people in the MOFs area, the big guns and even the not so big guns, they will have to really think hard about what these MOFs are going to be able to do. Otherwise, you'll just get more and more papers, and after some time people will not read all these papers, because in chemistry I've always found that unless there is a real need for something by society, by the public, by the companies, work doesn't get done. I mean, all of us know that Louis Pasteur discovered stereochemistry because he was asked to solve a problem in the wine industry in Paris. So when he started looking at those crystals of those tartrates that he was looking at, it's then that he found out that they were hemihedral, etc., etc. So he didn't go in there saying, let me find stereochemistry. He found it because there was a commercial need for him to come and look at that problem. So this is Haber's process, same story. They needed a quick way of fixing nitrogen because Germany had lost its supply of sodium nitrite in the First World War. So they had to do something very fast, otherwise they were going to be in big trouble. So Haber's process also started in the same way. So I think people in MOFs area really have to worry about this. Now, similarly, now using MOFs as a means of storing water, collecting water. See, vast areas of the world don't even need this. In India, the problem is, I don't know what it is in Russia. In India, there is enough water, but it all falls at only one time in the year, which is the monsoon. So then methods of water storage are more important than not having the water. And we have so many indigenous ways of storing water all over the country. And this Cheru place, that is where I'm actually standing in one of these places not so many years ago. And so each part of the country has its own way of storing water, collecting water when it rains and storing it for the time when it is dry. So each country will have its own problem. This is our 100 rupee note, and you can see a very elaborate well, deep well, this, with all these carvings and sculptures. It's not a museum, it's a place for storing water. It's right here, and it's called Vav in the state of Gujarat. See, I told you we are a civilizational state. Civilizational state means doing all this. It means not running behind mouths to, as a means of capturing water or something. And even in the desert areas where the MOFs have been proposed, and this is a half desert area, we still do quite well with traditional methods in India. So this is not to, say that everything old is bad and stuff like that. I think the challenge of science is to take these old things and put them out in a modern context. Coughs, I can go on talking, but the main problem with coughs, as Rahul Banerjee, one of the leaders in that area, has pointed out, scalability, stability, processability. For those who want to know more, please read his perspective article in JAX. Incidentally, it's so happy to know he's one of my PhD students who is now one of the associate editors of JAX. So you see, people are working on this, they're thinking about this, and they know he is a person who's worked on coughs for a long time, and this whole article is kind of very realistic. He says it's not so easy to get a product out of these coughs now. Now, similarly, the application of coughs. People will say all sorts of things. It does everything from cure cancer to, take you to Saturn. But, we have to also please put some realism in all this. Finally, solar energy, we come to this thing. And solar energy, functional materials. This is a huge topic. How does crystal engineering get into this? The energy cost is already falling by 70%, and by 2030 the renewable energy sources will be preferred. Solar energy, I mean, we have a lot of this thing in India, and today solar energy is becoming a really viable alternative. There are countries in Europe where people don't have to pay for electricity anymore. I don't know what the story is in Russia and what the alternate sources of energy are, but you'll have a lot of oil. So I think probably it will go on in that way. And so the idea is that the compounds to beat here are the perovskites. Just like I told you, MOFs have to beat zeolites. The organic solar energy things have to beat perovskites. Crystal engineering can feed design advances, because when you need energy conversion devices which need to be tunable, lightweight, flexible, and located in unusual and odd places where fabrication of shape is important, that is when these organics are going to come in to their own. And wearable electronics, sensor devices, these are all the places where the organics will come in, and they will probably, already perovskites are doing quite well. So, there is still some research that has to go on before you can do this. Now, talking about the crystal engineering part, what is done? The thing is that in these, let us take polythiophene as an example, PHT. It is one of these important materials for the photovoltaics. PHT molecules can assemble plane to plane, cofacial, or plane to edge. So this is plane to edge here, and then this is your plane to plane. So depending on what molecule you choose, for say for an hydrocarbon or something like that, fused molecule, you can either get the edge on or the face on configuration. So you need to know a little bit about the molecule, a little bit about interactions and the structure before you start getting into things. Once again, I would say, take property, go back to structure. If you want cofacial, you need certain kinds of molecules. If you want orthogonal, then you need certain kind of molecules. So this is the way really one would take it. So finally, as you can see, I have concluded 5-7 minutes before I said you would. And I'd really like to thank all of you for listening patiently. And in this COVID time, it is really difficult to speak. You can speak to anyone in the world. I'm speaking to you in Moscow. Yesterday, Victor told me it's -2 degrees there. Here it is +18 and we're all feeling cold. So it is quite cold for us in Bangalore at this time. So -2, we can't even understand what it means. But still, you see, this world is wide, but it's very nice to talk to all of you, but physically I can't see you. So, if I were to give the same lecture in Moscow, I would have been so much more excited, I guess. I don't know. So anyway, this picture is a special one for this audience because it was painted by a very famous Russian painter called Svetoslav Rurik, who spent most of his time, Nikolai Rurik, who spent most of his time in India in the Himalaya regions. So, yeah, Svetoslav was his son. So, Nicholas Rurik, about 100 years ago, he painted a lot of pictures on the Himalayas. And so I chose this one special for this talk to sort of give you a feeling for, the vastness of this world, the vastness of science, the vastness of the problems that confront scientists. Scientists have to worry more about themselves as a part of society. We can't sit anymore in our, what we shall call some sort of ivory towers and doing all sorts of things. Yes, to some extent, we have to do our work rigorously and so on. But on the other hand, we are part of a very much bigger picture somewhere else. And I think if scientists get this kind of responsibility, then I would feel that it will be good not only for society but also for science itself. So, with these words, I would like to thank you all very much, and I hope that this Microsoft Teams has allowed you to hear all this thing properly because it's something that I don't understand and makes me quite uneasy at times. So, thank you very much indeed. Thank you, Victor, for this nice invitation to come and speak to all of you.
Thank you very much, Professor Dizraju. Very brilliant talk. Are there any questions? The presentation is open for discussion. So please ask your questions, especially young scientists. A right chance to communicate with very famous scientist of modern days. I do not see any questions. Probably I'll ask one. Could you please comment when you go from binary to ternary and further to quaternary co-crystals? What power do you acquire? What is the reason to do that?
Yeah, we've written about this, but since you ask, the problem with binary to ternary is that suppose you take a mixture of any three compounds, you should try to avoid the formation of three different binaries. So if you have ABC, you don't want a mixture of AB, BC and AC in that stuff that crystallizes. You want one ABC together. So to avoid binary formation, because you cannot fish out ternaries out of a whole mixture of binaries and so on, there is what you need, an interaction hierarchy. You must have different interactions of different strengths. And the two strengths should not be very far away from each other and they should not be very close to each other also. Because let us take the two situations. When they're very far away from each other, you will only get binaries, you will not get a ternary. If they're too close to each other, you will get solid solutions like what Kitaigorodsky said. So it has to be very, very carefully calibrated. So if you have, and we found that a good combination for us in our hands was hydrogen bond and halogen bond. Because if you take our average NHO, OHO hydrogen bonds, it's about roughly in the region of 10 kilocalories, 8 to 10 kilocalories per mole. The typical halogen bond, even with the activated iodine and so on, is about 4 to 5 kilocalories per mole. So this looks like a nice gradation. If you made the second interaction too weak, like OHO and CHO, then you'll start getting binaries again. So, sir, this crystallization, co-crystallization, it is like all synthesis. It is a science and an art. You cannot have a menu and you cannot have a prescription and say if you do this, you will get this for all time. So any synthesis, I mean, synthetic chemists for the last 200 years have realized this and they have said this, that it is a science and an art. I would say that crystal engineering is also in that way a form of synthesis, as I've been saying for many, many years. It is a science and an art put together.
Okay, thank you very much. Anna Volokjanina has a question. Anna, please ask a question.
Please.
Hello. Thank you
Hello.
very much for a very brilliant lecture. Can you hear me?
Yes,
Yes,
you're
yes.
most welcome. Thank you.
My
Thank you for
question
your
also
comment.
concerns this type of multi-component crystals. If
Yeah.
you take also solid solutions into account, what is the maximal number of components you're lucky to obtain?
I'm glad. See, if you have solid solutions, then the number is no limit. Somebody in India has also got something with 11 things. And, when we went from 4 to 5 and 4 to 6, the way we did it was that the 4 of them was stoichiometric, and the fourth one we made a solid solution. So the fourth position had 1 of 2, and then if you make 1 of 3, you get 6. But I call that cheating. We're trying very hard to put 5 compounds stoichiometrically in one crystal. So far, over many years, this has eluded us. We may not get around to doing it, but I'm sure somebody will. There must be a theoretical limit on how many things you can get in stoichiometrically. Right now, I seem to think that 5 is the limit. But when Christer Akeroy first told us about the first ternary crystals 20 years ago, most people call this a curiosity. They said, oh, three different things in a crystal, it doesn't make any sense. It's very difficult. But now putting 3 together is quite easy for many people. And we have them in the hundreds. So it's 4 is already difficult, except for our group. I think nobody else has really been able to manage with 4. But 4 is I feel quite easily possible. 5 is going to be really difficult. It is like those Himalaya mountains I showed. uh, 20,000, 22,000, 24,000 feet high mountains. Each of them is an order of magnitude more difficult. So it's not just the number, but it becomes very, very hard at the stage of quaternary. Yeah.
And as far as I could understand, these compounds do not include solvent molecules. So which solvents do you use to avoid the inclusion?
Yes, you're quite right. You're quite right.
Do you use water or?
Water, methanol, all the standard things, ethanol. Nothing very fancy, you know.
Thank you
There's
very much.
another interesting thing about this. When you hit the right combination of compounds and solvent, you do not get the lower order co-crystals. So when you're trying for a ternary, you don't get binaries. When you're trying for a quaternary, believe me, you don't get ternaries. So there is a correct combination which drives you to exactly what you want. And this tells me that crystallization itself is a highly specific process.
It really looks like a kind of magic, I think. And it would be interesting to compare if the same synthesis in Russia under another room temperature will give the same results.
Humidity.
I know that for
even
chemists it's
very
always
nice that you
difficult.
say this, because we have found even with the smaller temperature variations in India, a crystallization that works in the hot season doesn't work in the cold season and vice versa. So this is something very interesting, and this is again, unreported observations. People don't like to talk about this because it looks like they're talking crazy. But I think there's a lot to it which has to be looked at more seriously.
Because it's true for coordination chemistry and for supramolecular chemistry, it should be even more pronounced effects.
Then I think Russia will be the best country to do this because the temperature variations are probably the maximum for you.
Thank you very much again.
Okay, let's thank our speaker for a very astonishing and brilliant talk.